Okay, so let's take a look at the divergence and the curl of the electric field. After some derivations of these things, we're going to look at Gauss's law. To be more exact, once we find the divergence of E, we'll be able to derive Gauss's law. We have a few preliminaries that we have to take care of, and the first is to show that the del operator in the r coordinate system is actually equal to the del operator in the funny r system. And remember that the funny r is equal to r minus r prime, where this represents a vector to a field point and this represents a vector to a source point. So when we put an r on there, that's our normal del that we've been using in the past. Well, to show this equality, we're going to take the Cartesian components of this vector and just call them these capital letters, capital X, Y, Z. And we've already used x, y, z for the components of the little r vector. Look at the definition of these. If you take the capital X component of funny r, that's what it looks like. Same goes for y, same goes for z. Well, going back to the r system, so this is del sub r, it's equal to partials with respect to x, y, and z, and I've written this as a column vector, but you see the partials with respect to x, y, z. We can write that as the partial of capital X, partial of x, and then the partial with respect to capital X, and likewise for y and for z. If we then look at our definitions of those capital letters, if you take capital X and differentiate it with respect to little x, you get a 1, and then minus the partial of the primed x with respect to this x. These two are independent, so that will be 0. Well, the same goes for y and z, and so you end up where you have these factors here, you're going to get a 1. So therefore, when you just substitute in the 1, you get the column vector, which is the partials with respect to the capital X, Y, Z's. So if you look over here, all we've done is replace these, so we would claim then that this vector, which is equal to this one, which is equal to this one, which is equal to this one, which is del of funny r. So we've actually shown this equality. So just to remind you, I put this equality up here. We're going to apply this little r del, making the divergence of this function right here. It's funny r hat over funny r squared. And because of the equality that we have here, we can replace the del with respect to the little r in terms of the funny r. And so we're going to use this equality now, where we have this function here, fairly soon. Earlier, we used the connection between the divergence of this particular function, which is little r hat over little r squared, in terms of this delta function. Okay, now this quantity here is the three-dimensional delta function. The delta function is used in association with an integral. So it has the property that I show you here, where instead of little r here, I'm going to put another argument, which is r minus r prime, the vector. So this is our funny r. The way this works is that when this quantity here goes to 0, then the integral tells you to evaluate the function, this scalar function here, at the position where this goes to 0. So that would be when r prime equals little r. And so what you do is you take this integral here, you say, okay, the thing that's left is the function itself evaluated where the argument goes to 0, which is when r equals r prime. Any scalar function of position, if we put it here in terms of the r prime and do this integral with the delta function, then we end up with this value here. If we come up here, you can see that the divergence of this particular vector function is equal to 4 pi three-dimensional r. And that's what this is, where instead of little r, we put in the argument r minus r prime. Okay, so if we now replace little r with funny r, it's the same deal. We have the divergence of this function again, but instead of little r here, we're going to put funny r. And that leads then to this property here, that you have this divergence is equal to 4 pi times the three-dimensional delta function at r minus r prime. So we're going to use that again soon. By analogy to divergence, we can write the curl in the same way. So if you just replace that dot with the cross, you would get the following. So we're just going to take this curl operator and replace it by this one here. And it's the same function that's in this position here, so therefore those are going to be equal. So now we're ready to attack. We're after the divergence of E. We have for a three-dimensional volume charge density, so here's our scalar function, by the way, rho of r prime. Remember, this is in fact the E field in terms of this general integral. So we're integrating the three-dimensional charge density evaluated at r prime, the source points, and we have the r minus r prime divided by its magnitude, and then we have the r minus r prime, the magnitude squared. This right here is our funny r, and this is funny r squared, the magnitude funny r squared. Okay, so we're just going to take this and operate on it with the r del. So here's our r del operating on E, and so that's equal to r del operating on this integral. So here it is right here. Funny r is equal to this, the magnitude of the funny r is equal to this quantity, and the unit vector in the funny r direction is equal to this. Coming back to the divergence of this integral, we're going to permute the del dot with the integral. We're going to bring the del inside the integral. So all we've done is switch the order of these two operators. This quantity here involves the partial derivatives with respect to the little r coordinates, as opposed to the r prime coordinates. But look at here, we have a function which is a function of r prime, and this is del r. So as far as we're concerned, this thing just is invisible, so we can bring it out and put it over here. So we say that rho r prime slips by the del operator. So here's what I've done. I put the scalar function evaluated at r prime over here, and we still have del sub r times this quantity here. You remember that we talked about this particular divergence before. So I've repeated the whole thing here. Here's our divergence that we're seeking, and here's the integral operator, and if we replace now the del of little r with del of funny r, because those are equal, then we're left with this equation here. So that's what I've just said. But now we have the del with respect to the funny r of this quantity here, and we can replace that with our three-dimensional delta function. The argument will be funny r, which is this quantity right here. So this is the three-dimensional delta function operating here. So when we put it in the integral, what will survive is when this equals 0. So it's one single value. That's the only value that we have to worry about. So we've replaced the divergence of this quantity here with 4 pi times the three-dimensional delta function. And so that will be equal to rho of r. So coming back here then, here's our divergence of E. So we have k times 4 pi. The 4 pi is this 4 pi right here. And then rho of r, which is right here. Rho of r coming out of that integral. The divergence then becomes, if we put in our k, 1 over 4 pi epsilon naught, times 4 pi rho, that's it. So we can simplify that by just canceling the 4 pi's, and we have then that the divergence of E is equal to the charge density evaluated at the same point divided by epsilon naught. And I put here that this is a big deal. Later we'll find that this is one of the Maxwell's equations. This has another name. It's called Gauss's law, the differential form, and so we'll refer to it as that also. What you see here is if there is a source function at the point r, so if there is some charge there, and so whatever value that has at the position r will give us a non-zero divergence. So if there is a source at r, there is a divergence at r. One outcome is if you know capital E sub r, then you can find the charge density just simply by taking that divergence. This is not common, but sometimes it's used. Well, this is such an important equation that we put it on a pedestal, so that's what I've done here. Try to remember this. Let's integrate both sides. So here's our divergence of E, and this is what that is equal to, the differential form. So if we integrate both sides with respect to volume, we can write this equality here. So it's the same volume here as it is here. But now we're going to use the divergence theorem, which I've given in general in terms of a vector capital A. And that is that if you take a volume tau and take the divergence of A within that volume, then that's equal to the surface integral of that vector over the surface. Here's tau and here's the surface. So if you integrate the divergence all within this volume here, that's equal to the surface integral of A on the surface of this volume. So substituting in E for A, we just have the divergence theorem here given for the E field. And the only requirement is that S bounds this tau. If we now introduce our right-hand side, which is the same thing that we have above, then we just have this integral here equaling to the surface integral. However, if we bring epsilon 0 outside, then we're integrating the volume charge density over the volume. And what that equals is just the charge enclosed by that volume. So we then have a very simple relation between the surface integral and the charge enclosed. That's what we call the integral form of Gauss's law, which is probably the one that you're most familiar with. If we look at this side of the equation here, that's related to the flux out of the surface S. And we say out because the ds vectors are all pointing out from the volume tau. So when you take the dot product, you're getting the component of the E field in the outer direction. Now obviously if it's negative, it'll point down into the volume. So here's our volume, here's our flux, and here's the enclosed tau. Don't forget this is a closed surface, so there will be field lines going into the volume and there will be field lines coming out. The total of all of that flux is what you're measuring here. So to restate it, the flux of E passing through a surface S is defined as this integral right here. This does not have to be a closed surface, but if it is, it's still correct. The total flux out of the volume tau passing through the surface S, Gauss's law says it's the total charge enclosed divided by epsilon 0. Most frequently, this particular relation is called Gauss's law.